Hello, this is Jack Jackson. In this video, we're going to talk about integrating rational functions using some algebra of fractions. So if you're going to integrate a rational function, if it doesn't work with just a straight substitution, then if it's an improper fraction, the degree is larger in the numerator than in the denominator. Okay, the degree in the numerator is greater than or equal to, I should say. Okay. Then the first thing you want to do in that case is use polynomial long division to write the improper fraction as a polynomial plus a proper fraction. Then, if simple substitution still doesn't work on the fraction part, apply partial fraction decomposition. And this should break down the original integral into the sum of integrals, for which we can use some earlier techniques, perhaps simple substitution, perhaps trig substitution. So let's look at a couple examples of that. So 3x cubed plus 22x squared plus 53x plus 39 all over x squared plus 6x plus 9. And we want to integrate that. Find the family of antiderivatives. Well, notice that first of all it's an improper fraction. The degree in the top is 3. The degree in the bottom is 2. So the first step is to start doing some long division. We write the numerator down here as the dividend in decreasing order, 3, 2, 1, 0 for the powers of x. Decreasing order for the divisor, which is the denominator. And we divide out. 3x cubed divided by x squared is supposed to be 3x. How did that go 2? Get that fixed. Okay, so we fixed that, so it should be a 3x. 3x times x squared is 3x cubed, which has to be the same as what we have. 3x times 6x is 18x squared. 3x times 9 is 27x. Change the signs, which I've given the change sign in little boxes here, and add using the change signs. So this cancels out. 22x squared plus a negative 18x squared is 4x squared. 53x minus 27x is 26. And we have our 39 we bring down. 4x squared divided by x is 4. 4 times x squared is 4x squared. 4 times 6x is 24x. And 4 times 9 is 36. Change the signs, all negative in this case. Add, this cancels. 26x minus 24x is 2x. And 39 minus 36 is 3. So we have a quotient and a remainder. And so that means we can take our fraction, improper fraction, and write it sort of a mixed number type form, similar to a mixed number. We have a polynomial, 3x plus 4, plus a proper fraction. Now when it comes time to integrate, integrating this polynomial part is going to be pretty easy. The fraction part, well, maybe we need to do something with that. So we're going to do okay, so let's see. We have now the quotient was 3x plus 4. The remainder was 2x plus 3. So the original fraction is 3x plus 4 plus 2x plus 3 over x squared plus 6x plus 9. Now that we have this in a proper fraction, and only after we have it in proper fraction, we can do partial fraction decomposition. So this is, take the proper fraction, 2x plus 3 over x squared plus 6x plus 9, factor the denominator, which is x plus 3 squared. In this case where you have the multiple power here, bigger power 2, you have to list the x plus 3 and the x plus 3 squared as separate things, but then the coefficients are just going to be constant terms because these are linear factors, even though this one is squared. Now, multiply both sides of this last equation by the x plus 3 squared, so the original denominator cancels, leaving only the original numerator on the left. On the right, we distribute that. One of the x plus 3's cancel, leaving us an a times the x plus 3, plus, then the x plus 3 squared times this one cancels, leaving us just the b. Solve this by annihilating the a by putting in x equals -3, makes -3 plus 3 0, so this term goes away. So it leaves only b on the right. On the left, we have -3 times 2 is -6, plus 3 is -3, so b is -3. Now I can substitute that in place of b as -3, and I can't annihilate the b, but I know what it is. So the next easiest thing to substitute in would be 0. So I plug that in, although I could have plugged in any number to give us the same result. I'm going to plug in 0 here for x, so 2 times 0 is 0 plus 3 is 3. 0 plus 3 is 3 times a is 3a, and we got the -3. Add 3 here, we get 6 equals 3a. Divide by 3, a is 2. So this is 2, the b is -3. That means the original integral, the integral of this, what we started with, is here. That fraction is 3x plus 4 plus, I'm just going to factor it out, the 2 times 1 over x plus 3 minus 3 times 1 over x plus 3 squared, and each of these parts can get its own integral. The integral of the 3x, use the power rule, goes up to 2, divide by the new power, so that's 3/2 x squared. Integral of a constant just picks up a factor of x, so that's 4x. And here we do a substitution. Let u be x plus 3, du is dx. The integral of 1 over u du is the logarithm, natural logarithm, of the absolute value of the u. So this is still got the 2. So it's 2 natural logarithm of absolute value of x plus 3. And this last one is, say, w. Well, I could say u again. It's the same u as I had here. Say u is x plus 3. So this is u to the -2. du is dx, so we don't have to worry about that part. So u to the -2, let's see, we add 1 to the power, that's u to the -1, and then times the derivative, derivative of the u, which is just, I'm sorry, we already have the du. It's just divided by the new power, which is divided by -1. So that's going to make this positive 3, and then x plus 3 is u. So we had u to the -1 is 1 over u, so this becomes 3 over x plus 3, and then we add our constant. Okay, maybe you should try this one yourself here. Let's try 41 on your own. Press pause and come back when you're ready. Well, this time we don't have to do the long division because it's a proper fraction, but we can factor the denominator by grouping. Group the first two terms plus group the last two terms. And the first one we can factor out an x squared, leaving us x minus 3. And the last part we can factor out a -1, leaving us x minus 3. Now we can factor out of this basically a more or less a bigger binomial at this point, two terms. We're going to factor out an x minus 3, leaving us an x squared minus 1. X squared minus 1 factors as x plus 1 and x minus 1. So when it's all settled there, the denominator factors as x minus 3 times x minus 1 times x plus 1, and we still got 2x plus 5 on the top. 3 linear factors, so that just gives you, each one gets its own fraction here without the denominator. They're all linear factors, so we just have constants for the numerator. So we get a over x minus 3 plus b over x minus 1 plus c over x plus 1. Multiply both sides of that equation by the common denominator on the denominator on the left, and you get just, that cancels out, leaving 2x plus 5 on the left. Distribute on the right, we get an a times x minus 1 times x plus 1 plus b times x minus 3 times x plus 1 plus c times x minus 3 times x minus 1. And let's annihilate some stuff. I'm going to start by plugging in x is 1. That's going to annihilate the a and the c. Make those terms both go to 0. 1 minus 3 is, that should be -1. Let's see if I can fix that. So that makes that a -2. 1 minus 3 is -2. 1 plus 1 is 2. 2 times -2 is -4b. That's the one side. The other side is you plug in 1 here. 2 times 1 is 2 plus 5 is 7. So -4b equals 7. b is -7/4. All right, let's annihilate some stuff by putting in x equals -1. That's going to wipe out the a here. It's going to wipe out this term. So both of those are 0. -1 minus 3 is -4. -1 minus 1 is -2. So that makes 8c, positive 8c. Another sign mistake. Oh my goodness. All right, that's fixed. So 8c equals 3, so c is 3/8. And finally, if we plug in 3, that will wipe out this term and this term, so they're both 0. And the only one left is the first one here. 3 minus 1 is 2. 3 plus 1 is 4. 2 times 4 is 8, so we get 8a. And 3 times 2 is 6, plus 5 is 11. So 8a equals 11. A is 11/8. That must have been a copy-paste problem there. Okay, so we see that originally we had 2x plus 5 over x cubed minus 3x squared minus x plus 3. That's 11/8 over x minus 3, -7/4 over x minus 1, and 3/8 over x plus 1. So the integral here on the left is just broken into 3 integrals. These a, b, and c, I'm just factor them out and then pull them out front of the integral sign. So that's 11/8 integral of 1 over x minus 3 dx minus 7/4 integral of 1 over x minus 1 and 3/8 integral of 1 over x minus 1. And whether we let u be x minus 3, x minus 1, or x plus 1, du is dx. So all of these just become basically the integral of 1 over u du for different substitutions of u. So the antiderivatives are just log of the absolute value of the denominator. So what we end up with is 11/8 natural logarithm, the absolute value of x minus 3, minus 7/4 logarithm, the absolute value of x minus 1, plus 3/8 logarithm of the absolute value of x plus 1. And of course, when the last integral sign disappears, don't forget plus c for the arbitrary constant so that we have the entire family of antiderivatives. In our textbook that we're using right now, Larson and Edwards, it's on section 8.5. You should have a section on this in whatever calculus textbook you're doing. So go ahead and read that textbook now and look at your examples, and then have some practice doing some homework problems for my students. At least this semester I'm recording this. This is going to be the first 10 problems or so from homework set 1.3.